Welcome to the deep dive. Today, we're doing a real strategic analysis of the factory floor.
Yeah, getting right into the nuts and bolts.
Literally. Because if you've ever had to source a high-performance part, you know that the first choice, the biggest choice, is how you're going to make it.
Right, how you turn that lump of raw material into a final component.
And that one decision really determines everything. The cost, the speed, and whether the final product is actually going to hold up under stress.
It's the whole ballgame.
So that's our mission for this deep dive. We've been looking at sources comparing the three big manufacturing families: subtractive, additive, and formative.
We're looking at the physics, the economics, and all the new digital stuff that's changing how we make things.
Exactly. And the goal is to give you a kind of mental shortcut, a framework for understanding the strategy behind it all. Like why a really complex part can sometimes be cheap.
And why getting that last little bit of precision can cost you an absolute fortune. Our goal really is to get past the buzzwords.
Right.
And just uncover the fundamental rules for making that decision. Because it's always this balance of three things. How complex is the geometry?
Okay.
What kind of mechanical performance do you need? And of course, what's the volume? How many are you making?
All right, so let's start with the most basic difference then, the material itself. How do these three families approach the raw stock? And how much of it do they, well, waste?
It all comes down to how they handle that initial block of material. So subtractive manufacturing or CNC milling, lathing.
The classic way of doing things.
Right. It's conceptually very simple. You start with a block and you just cut away everything that isn't your final part.
So it's fundamentally wasteful from the get-go.
It is. I mean, the material is removed by shearing, which creates all these scrap chips and offcuts. And even if you recycle them, you're starting with a material efficiency deficit.
Then you have additive manufacturing, AM, which just flips that on its head.
Completely. Yeah, AM has the highest material efficiency you can get, really.
Because you're just building it up.
You're building it near net shape, layer by layer. You only deposit material exactly where you need it.
And what about the third one, formative?
Formative processes. So this is forging, stamping, that sort of thing. They're also super efficient.
How so?
Because they don't remove material. They redistribute it. They use force to change the shape without changing the volume, which means you get minimal scrap.
Okay, here's where it gets really interesting for me. The design flexibility. AM seems to have this, unparalleled freedom.
Oh, absolutely.
We're talking about things like internal lattice structures or these super complex cooling channels, things you could never physically machine with a traditional cutter.
That geometric freedom is AM's single biggest advantage. It's revolutionary, but, and this is a big but, it comes at a cost in terms of material reliability.
So SM and forming are still ahead on that front.
They hold a significant advantage, especially for parts that are under high stress or in high temperature environments.
Why is that?
It's all about material uniformity. The integrity of the internal grain structure is it's paramount.
And the sources really hammered this point home. For safety-critical parts, things like landing gear or parts for a car's drivetrain, formative processes like forging are often mandatory. Why is that?
It's about engineering the strength right down at the microscopic level.
Okay.
Think of it like a piece of wood. It has a grain, right? If you cut across the grain, it's weak.
Sure, it'll snap.
Exactly. But if you can bend the wood so the grain follows the curve, it stays incredibly strong. Forging does that with metal. It physically redirects the metal's internal grain flow to follow the shape of the part.
So you're not cutting across those lines of strength.
You're aligning them for maximum performance. This gives you dramatically better fatigue resistance than you'd get by cutting across the grain or, and this is key, by fusing powder together layer by layer like in AM.
So if a part has to survive millions of high-stress cycles, forming is the only real choice.
Typically, yeah, it gets the mandatory nod.
Right.
Which brings us to a really important question about cost.
Which is?
When does complexity stop being expensive?
In the traditional world, with subtractive and formative, complexity is always the enemy of your budget.
Always. More complexity means you need more expensive tooling, or it just takes way, way longer on a complex CNC machine.
But with additive manufacturing, that whole cost model just changes completely.
It's a total paradigm shift. The cost is driven mostly by two things: how much material you deposit and how long the machine takes to do it.
Which means the cost is What? Independent of how complex the part is?
Pretty much. Yeah, it's relatively independent of geometric complexity. You can print a simple solid cube or a really complex lightweight lattice structure that uses the same amount of material.
And takes the same amount of time.
And the machine time cost is basically the same. That is the core economic disruption of AM.
The perfect example of that must be something like an internal heat exchanger.
Absolutely.
Trying to machine those intricate little internal cooling channels would be just prohibitively expensive.
But printing them, even in some complex fractal pattern, is functionally free from that complexity cost perspective.
But there's always a catch. You mentioned it earlier, the hidden cost.
The hidden cost of finishing,
Yeah.
post-processing. It's a massive, massive bottleneck in AM.
So tell us why. Why is that stage such a problem?
Well, AM parts, they just don't come out of the machine looking pretty. They typically have a really rough surface texture.
Okay.
So to get the smooth finishes you actually need for performance, say for a surface that needs a seal or an aerospace part that needs minimal drag, you need secondary operations.
And that's where you get into measuring surface quality
Mm.
with, what is it, raw?
Yeah, raw. It's the arithmetic average of how much the surface profile deviates. A low raw value means you have a very, very smooth, precise surface.
And getting to that low raw value on an AM part is the hard part.
It is. It often requires things like vapor smoothing or chemical etching or sometimes just manual mechanical polishing.
Which sounds very labor intensive.
Extremely. And it often just completely negates the speed advantage you thought you had with AM. It inflates the final print-to-part costs and the time it takes. Suddenly, your finishing bay is the bottleneck, not the printer.
Okay, let's pivot back to subtractive for a minute. We've said it's resource intensive, but it delivers on reliability. And when you want ultra accuracy, SM is still king. So how do engineers control that process, the physics of just shaving off tiny bits of metal?
The key metric there is the material removal rate, or MRR.
MR.
It's the core formula for speed. The volume of material you remove per unit of time is calculated as RMR equals V times F times D.
So that's cutting speed times feed rate times depth of cut.
Exactly. But that simple little equation contains this critical trade-off.
Yes.
If you want to go fast, you want a high MRR, you crank up V, F, or D. But if you push them too high, you generate a ton of heat, the cutting forces go up, tool vibration increases.
And your surface quality just goes out the window.
Completely. You get chatter, and the finish is terrible. It's a really delicate balance.
So the smart way to do it isn't just to max everything out. The sources talked about a two-stage strategy.
Precisely. You start with the roughing stage.
Okay.
Here, speed is everything. You use a high depth of cut, or D, to just remove the bulk material as fast as possible. You accept that you're going to get a poor finish because the only goal is high MRR.
Get the basic shape cut out.
Right. Then you switch to the finishing stage, and here you do the opposite. You dramatically reduce the feed rate and the depth of cut.
You increase the cutting speed, V.
Often, yes. You're sacrificing MRR and speed, but those smaller cuts minimize the heat and the force, and that allows you to hit that critical dimensional accuracy and get the surface texture you need.
The goal flips from speed to just pure quality.
Totally.
And the financial side of this is, it's huge.
Yep.
Going from a standard CNC tolerance, maybe plus or minus 0.05 millimeters,
Yeah, pretty standard.
to an ultra high precision, something below plus or minus 0.01 millimeters. That's not a small price jump.
It's not linear, it's exponential. The tooling, the machines, the time it takes to inspect the part, it all just skyrockets.
So standard milling can get you a good finish, but for something really, really smooth.
For a good finish, say 1.6 to 3.2 microns raw, standard milling is fine. To get tighter, down to maybe 0.4 microns, you need precision grinding.
And for the absolute tightest tolerances,
Yeah.
the plus or minus 0.0002 millimeters.
Then you're forced into highly specialized processes.
Like what? Honing and lapping.
Exactly. Honing, lapping, superfinishing. These are processes that use controlled abrasion with special compounds to remove just micro layers of material. They take a lot of time, a lot of labor, and they represent a massive cost increase.
So the takeaway for a designer is, make sure you actually need that level of precision.
Please, yes. Unless the part's function absolutely requires a 0.4 micron raw finish, you're just adding zeros to the invoice for no reason.
So what happens when standard subtractive machining hits a wall? Like with really hard materials or complex shapes where a cutter can't reach. And we know AM struggles with reliability. What fills that gap?
That's where you enter the world of non-conventional machining, and specifically a process called electrical discharge machining. EDM.
EDM.
EDM is totally different. It removes material by melting or vaporizing it with a controlled electric arc. There's no mechanical contact at all,
Wow.
which means it can achieve these ultra-fine surface qualities. We're talking raw values down to zero point 0.1 microns and incredibly tight tolerances.
And since there are no cutting forces, I guess it's perfect for really hard stuff.
It's the go-to process for machining hardened tools, molds, and dies that would just instantly destroy a conventional cutter.
Okay, let's circle back to AM in this high-performance world. We're always hearing about 3D printing replacing traditional parts. What are the material science hurdles it's still trying to clear for those really mission-critical components?
Well, you have to remember, AM isn't just one thing. There's VAT photopolymerization like SLA for high-detail parts. There's FDM for basic prototyping. And then there's powder bed fusion, PBF or SLM, which is what's used for the high-strength metal parts. And that's where the primary struggle is. Material uniformity.
Because you're fusing layers of powder together.
Exactly. You're creating boundaries between each layer.
Oh.
And this layer-by-layer structure, it often causes something called anisotropy.
Anisotropy.
It just means the mechanical properties, like tensile strength, are different depending on the direction.
So if you stress the part along the z-axis, the direction it was built in, it could be weaker than if you pulled on it from the side.
Precisely. That potential weakness along the layer boundaries is a huge reliability concern for regulated industries.
So how do engineers deal with that?
They have to try and compensate. They run a lot of pre-build simulations, and they try to orient the part on the build plate in just the right way to minimize stress along those weaker lines. It's a compromise that something like forging just doesn't require.
Okay, let's shift gears completely. Away from the machines themselves, what are the digital technologies that are really changing the game here?
The big one is virtual manufacturing, or VM.
Yeah.
Basically, it's using digital models and simulation, what we call virtual prototyping, to predict how a part or process will perform before you commit any physical resources.
And what's the engine behind that predictive power?
It's a tool called finite element analysis, or FEA.
FEA.
What FEA does is it breaks down a 3D model into this mesh of thousands of tiny little elements. Then it can mathematically analyze how the whole thing reacts to physical forces, whether that's stress or vibration or heat.
And that saves a lot of trial and error.
A huge amount. We saw sources showing that using FEA to simulate the complex way metal deforms in forging can reduce the number of expensive physical mold trials by about 25%.
That's an immediate return on investment.
Right away.
And the ultimate evolution of this seems to be the digital twin. We hear that term all the time. What does a digital twin do that a simple FEA simulation can't?
So a digital twin it's much more sophisticated. It's a live, highly accurate digital replica of an entire system. Not just a part, but maybe a whole machine or even an entire factory floor.
And it's fed by real-time data.
Constantly fed by real-time sensor data. And this enables something called virtual commissioning.
Okay.
So instead of running a few hundred simulations, you can run thousands of what-if scenarios in parallel without ever touching the actual production line.
That's incredible.
We saw this great example of an Italian manufacturer that used a digital twin to simulate and rearrange their whole production sequence. They found and fixed these costly bottlenecks before they ever happened in the real world.
So IT and data science are now just as important as the person running the machine.
They're fundamental to maximizing efficiency on the shop floor. Absolutely.
Okay, so let's try and bring this all back home for you, the person listening who has to make these choices. It feels like the decision is driven by three core connected factors.
That's a good way to put it.
First up, complexity versus cost. Additive manufacturing makes really complex shapes functionally cheap.
Right, but you have to look past that initial print cost.
You had to calculate the very real, often manual post-processing costs to get the performance and the finish, that low raw value that you need.
The second one is performance versus precision. For absolute strength, for that superior grain structure, formative processes like forging are often the non-negotiable standard.
And for that extreme dimensional accuracy, you're going to pay a steep premium for specialized finishing or non-conventional methods like EDM.
And the third factor is volume.
Volume. Low volume runs prototypes. That's a perfect fit for the flexibility of AM or CNC machining.
But once you get into high volume production, we're talking runs over, say, 10,000 units, that's when it makes sense to make that massive investment in tooling for formative processes.
And underlying all of this, something we have to mention, is safety.
The foundation must always be safety. And as manufacturing gets more advanced, the hazards actually change. Well, modern production has these really specialized risks, like the very serious explosion risk you get from fine, reactive metal dusts in additive manufacturing environments.
So the single most disruptive element here isn't one machine or another. It's the synergy, this connection between the virtual world and the physical shop floor.
That's it. The real optimization isn't just cutting faster, it's about this seamless, predictive, data-driven synchronization of the entire system.
Okay, so a final thought to leave you with. We've established that the cost of precision just skyrockets below a certain point. But these digital models, FEA and digital twins, they're getting so good that they're eliminating the risk and cost of physical trial and error.
Right, they're making it more predictable.
So if they become so predictive that they all but eliminate physical prototyping risk entirely, what's the next thing engineers will focus on optimizing, beyond just precision and cost?
That's a great question.
Is the future of design going to be dictated solely by the physics of the material, or by the sheer volume of data we can collect about how that material behaves in the real world?